think we should go ahead and get started. It is my absolute pleasure to introduce Dr. Mike Puso to the FEM at LLNL seminar series. He's been at the lab since 1994, from what I can tell in my internet sleuthing, working on the lab suite of world-class engineering codes, specifically Paradigm, Nike, and Diablo. And today he's going to be talking about exactly that, current research here at the lab, particularly with regards to immersed boundary methods and time integration schemes. So I am very excited to hear this talk, and thank you all for attending. And with that, Mike, take it away.
Thanks, Jamie. Yeah, so today I'm going to talk about this, basically what amounts to interface mechanics and some of the projects that are related to that, and some of the research topics in those areas. And of course, these are some of the colleagues that produce some of the work you see here, but there's lots of people all involved in these different codes in the background and so on that are supporting this work. And so the mechanics of these interfaces come in lots of forms, either physical or computational. So contact and fracture would be physical, and then these immersed boundary or embedded interfaces or so on, could be either of them. And one of the work we're doing in contact is Tribal, which is a modern software library for modeling contact, in particular focusing on higher order discretizations that come from FEM. And some of the initial implementations are like in BLAST. Here's a result courtesy of Kenny Weiss. We're using the BLAST physics code and cubic element mesh. It gets nice smooth results. We've implemented this prototype in Diablo, L3D, and in Smith. Smith is this next gen engineering code that Jamie heads up, and that's combining FEM and Tribal into this engineering multi-physics code. And the focus on there is in particular on optimization, and most likely with LIGO. Our legacy engineering production code is Diablo, and we've coupled that to Tribal, and this is a result from our contact obstacle course. And so we ran Tribal through the contact obstacle course, and it was successful. We successfully hardened for the lower order elements, at least at this point. And then L3D, Ben Liu is working on the parallel domain decomposition for Tribal. We have at the lab GEOS, which models hydraulic fracture with cohesive zones in contact and interstitial fluid, and that's headed up by Randy Sedgas. One of our earlier immersed boundary codes was coupling our hydrocode Paradigm to Gemini, which is a Navy code, and there they use finite volumes in the background and then structural shells, and they're modeling blasts on ships. The current thing over the last 12 years or so is and now we have a production version of Fusion that has been used quite a bit over the last few years. It couples L3D, Paradigm, and the SPH code Spheral, and that uses cut cells in the background and it couples with Lagrange multipliers, and I'll talk more in detail about that. And then there's the an LDRD that's using this displaced boundary method that was developed by Guglielmo Scavazzi from Duke. And the Fusion stuff in particular, we're interested in modeling like a fracture or fragmentation. So you have blast going off. This is a grenade model by Chad Noble, and the gases, HE gases, basically project the fragments out, and you get a lot of contact with the fragments and so on. So with these interface methods, you have to come up with some sort of traction to enforce some displacement or velocity constraint at the boundary. And there's three basic flavors for that. You'd have a penalty or a Nitsche method, or Lagrange multipliers, which we'll talk about today, which for a variety of reasons I like better than this one, but I think more can be done there in the Nitsche world. And so in the Fusion, we use these multipliers, but then you have to incorporate advection, and then we're extended to SPH, and I'll go into some more detail about that. The flavor of the day for contact, for a variety of reasons, because it's very smooth and has really nice behavior, is this Moore contact. And unfortunately, it's biased. You have to choose a side, so you can't do self-contact problems. But we implemented 2 paths, and then we have to stabilize it. So I talked a little bit more about that. And then whenever you have like contact gaps opening and closing, in an implicit time integrator in particular, it'll drive it crazy and it'll go unstable if you don't do something special. In this case, we incorporate what they call structure preserving. It can conserve linear and angular momentum and energy, and I talked a little bit about that. So I'm going to, occasionally delve into some equations, and I'll try to move through them real quick because not everybody has that much of a tolerance for that. So with immersed boundary methods, you have an overlapping discretization. It would be a solid on top of a fluid or another solid. You might have shells, and you might even have SPH particles sitting on top of the background. And that obviates this conforming mesh, which is very complicated to build. This is easier to build. This is the easiest to build, which is a shaped-in mesh. But then you run into problems in these mixed zones where you have solids mixed with air. And there's a zillion different works, all started back in '64 with this coupled Euler-Lagrange method that was developed by this guy, William Noe, or Bill Noe, as they know him as, worked at the lab for a long time and also came up with a lot of good stuff. But that precipitated a whole bunch of other works because it's really powerful, and each one of these different approaches has sort of a different tact. Our tact was, we didn't want to have a penalty method. We wanted to come up, we do most of this immersed boundary stuff with explicit time integration. We wanted to come up with a good way to characterize a time step that isn't affected by the interface. So one of the issues we have to deal with is how to choose our pressure space. We have to solve for these multipliers. Unfortunately, we have to solve for them, that part implicitly. So there we have to look at the condition number of the system. And then, how do we get this time step? And since we use a time splitting AL, as most people at the lab know, you have a Lagrange step, and here we have to modify that for the constraint. And then the advection step, we have to restrict the flow at the boundary of that foreground and the background. And a lot of the details are in these papers here. So to start with, you have this foreground mesh that's in brown, and then this background mesh here that's in blue, and then you have the interface. And here's the equations. I put the linear equations in motion up, and you have these pressures that basically enforce this velocity constraint. B is for background, F is for foreground. This is your velocity constraint along the boundary. And these pressures, the way we choose them is they're piecewise constant. So everything in this cell, I have lambda1 integrated along this boundary. That gives me these B matrices. And then lambda3 along this boundary, and so on around. And the problem with that is you can get under certain symmetries, you can get this checkerboard mode, this -1, 1, -1, 1 pattern. And the reason why you get that is because when you average when you come up with the forces at these nodes, they're 0 because of the symmetry. So the way you get rid of that is you can stabilize it. Now I can pick this matrix, using this J matrix here, which basically penalizes the jump between all these guys. Okay. And that'd be a stabilized multiplier method. But for the sake of illustration, I'll also put in this penalty term, which will go away when I make alpha big. Now we're using central difference method to do the time integration. Okay. And that's used in this set of equations up here. It gives you this matrix. Okay. And the forces live on the right-hand side for because this is sort of an explicit time integration. These are diagonal mass matrices. And so I have to solve for this lambda. So what I'll do is I can condense this whole system out real easy because these are diagonal matrices, and get this small matrix H, which I just solved for the surface multipliers. Okay, and this H turns out to have a really nice quality that its condition number is independent of H, and you can show that from scaling arguments on these terms in H. Now this C matrix. Well, first of all, I can take this system up here and write it as a single equation you see here. And this C matrix, I I can solve for basically the inverse because of this alpha, and get what amounts to be a damping matrix. And it turns out there's a recursion that governs this equation here that looks like this. And it bounds the accelerations at time n and Vn by the initial accelerations, under the conditions that there's no, say, applied outside loads. And if K, which is positive semi-definite, and if A is positive definite, then this is a bound. These guys can't get any bigger, right? A's got to be positive definite. What is A? A is just a combination of the mass matrix, this damping matrix here, and this stiffness matrix here, okay? So this is positive definite. Turns out this is positive semi-definite, even in the limit that alpha goes to infinity. And so when I'm just using J, it's still positive semi-definite. So I can just throw that out of the time step calculation. I don't need to calculate it. It doesn't hurt my time step. And then K is positive definite, minus K is not. So I got to make T small. And so I just use the standard argument, the Rayleigh quotient, which can do that, which can give me that. It figures out the frequency for the system, and then I can figure out what the critical time step. And I can bound this by the worst element. And that's what we always do. So in this case, the worst element, well, this is a cut element, but it's not really a sliver because it's still a big element. It's just partially filled. And so the volume of, say, the material in this cut part is the same as the volume, the material you're using for the stiffness. So in that calculation for the worst element, that volume term cancels out. So this element doesn't hurt you any more than any other element. So the worst element may or may not be at the boundary. And they're not slivers. So if you run these problem out long enough, you can get a static solution. So I have this stiff inclusion here on some soft matrix. And this is a conforming mesh result. This is when you use unstable multipliers, and this is when you use the stable multipliers. And so you want to look at the convergence rate for this. And you get the optimal convergence in the displacement norm for the stabilized one. But this is the energy norm, and that's optimal. But you get this non-optimal for the unstabilized. So now, how do I do the advection? So, it's again, it's a two-step AL we're using in the background, and we can also do it on the foreground too, but using in the background. So you have the solid mesh underneath it should be void, okay? And here's a cut cell, and it has some material in it, DE. I do a Lagrange step when I push on it, so the whole thing just kind of compresses together. I enforce the constraint during that Lagrange step. Now I want to relax the mesh. So then when I relax the mesh, I get this volume flux from the right side, but I don't get any volume flux on the left side because I have what they call a PLIC, piecewise linear interface reconstruction, that says don't advect any volume flux at the interface. And this could be at an angle or anything like that, and the PLIC respects that. And so then I move on to the next step and go on. And then the whole time, just the void should stay underneath there and nothing should leak. So then we do some V and V, basically just comparing conforming to the immersed. So here I have a shock, a blast in this tube. It's a shock tube. You get a shock wave. We have tracers at intermediate points along here, and then I measure basically the pressure at those tracers between the immersed or embedded mesh with the conforming, and it matches up at all the different tracers quite well. Here's a buried mine. I have a mine in soil, and this is part of some work we did for the DoD for underbody blasts. And the blast goes off, and then we model the velocities at points on the plate, and then the dotted red matches the solid red for the embedded and the conforming, and the same thing with the blue quite well. And then here's a shell pipe. Blast goes off, the shell collapses on itself, as you see here. This is the displacement at a point in that shell, and for the embedded, you can keep modeling it indefinitely. For the conforming, basically it stops because you get a lot of mesh tangling in there. You can only do so much, mesh relaxation. So here I have two plates, and I have a fluid in between them. I give them an initial velocity. They come together. When they pull apart, there's void, and then the fluid collapses inside the void, as you would expect. And so when you look at the velocity of those two plates, say with the conforming mesh in the red, the velocity slows down as the plates come together and you squish the fluid, but then eventually stops because those elements get too small. They shape these plates in, it comes, they hit, and then they basically get advection welding. They glue together because they're not going to have any elasticity to them. There's no contact. But with the embedded, they actually do contact. Here we're using the common plane algorithm for the contact in ALE. It's a penalty contact, but it works well for this case. And then the plates rebound. Okay. Because we're going to want to model lots of frags, because this is what we do with this stuff, and these frags come in contact with each other. So this is a V&V that John Christensen did. You have these steel frags and this HE. The blast goes off, it pushes these frags out, and they want to keep these frags as a clump. They built this apparatus to measure this, the velocities and the locations of those particles. And it turns out it matched pretty well for what the results they were considering were within 1% of what they saw from the simulation and the actual experiment. So this is the nimble vessel analysis, which we're working on quite a bit. This is a simple version of it, actually. They have this pressure vessel. This is half of it. They put these screws in and they preload everything. So they run everything statically in Diablo, and then they hand it off to basically the coupled paradigm ALE code fusion, and the blast goes off, and they want to look at the pressures and bolts. There's lots of contact surfaces all over the place in this thing. We do a strong scaling study on this particular problem, and so here's the result for the embedded grid over the number of processors, and it's a strong scaling study, so it eventually bends over. This is if you decouple of it all, and so basically the foreground mesh is doing nothing, so that's real cheap. And if the model is not super huge, it's 1 million foreground zones, a lot of Moore contact segments. We're doing in paradigm foreground, Lagrange multiplier with the Moore on all these, basically at all these joints. And there's about 30 million background cells in ALE. Most of the work is actually finding where those overlaps are and then computing the weights. Turns out that solving for the multipliers isn't really hardly the cost at all. Because that condition number is very nice, we can just use a regular CG solver. We don't have to use multigrid or anything because, again, the condition number is independent of age. And the contact and the PLIC are about the same cost. The PLIC is the interface reconstruction for the multi-phase fluids and the modeling the advection near the foreground. Now, when we have a SPH is just a cloud of points. Or particles. They basically communicate with each other using these kernel functions, which are these smooth functions, which are circles or ellipsoids in 3D. And now we need an airtight surface to couple the background to the foreground. And so the way we get one is we identify points in the background that live underneath these kernel functions. And then for cells that are basically going to be cut because they have a red dot and blue dots in them, we put, say, triangles in them or tets, and we figure out, where these kernels cut these edges. And then, for 3D, we're going to put in triangles in those locations. Here we put lines and connect the dots. And here's a result in 3D. So we have these point cloud. It's immersed in this grid. And this is the triangular mesh that we produced out of that using this algorithm. And all this SPH stuff that I'm presenting is in this paper from a couple of years ago. And so the coupling is very similar, except we calculate the forces instead of using finite elements. We just use SPH. The SPH calculation for forces, which depends on these particle-to-particle force calculations based on the stress. These are the masses, and so you get what looks like the same equations of motion. These forces live over here, and I still have to calculate these multipliers to enforce this constraint that I just built along this edge. The background forces are computed the very same way, using finite element shape functions integrated against the pressures. But the foreground are different now. I don't have finite element shape functions for those, but I can create some, okay, and just use virtual work to basically do the coupling for the SPH and the background. So, but they have to be bigger than the kernel functions so they intersect the surface. And I just use the kernels and I expand them out. These kernels, I expand them out and then I weight them to basically make them a partition of unity. And that's how we do the coupling. And so here I got a blast that goes up, hits this SPH beam. The beam flies, and it compares well, about as good as you can get with SPH, because it has some accuracy issues. The plate flies and compares well with the immersed boundary, and the immersed boundary compares well with the conforming, so everything's good in those cases. Here's some results by Carly Spangler, and basically you have a bullet here intersecting glass or impacting glass. And we look at the residual velocity, and it compares quite well for the immersed SPH to the test results for different striking velocities. And this is basically the velocity after it leaves the glass. This is the damage. This is the actual glass. Here's a copper rod impacting an aluminum block. The analytical solution for the depth is that. Based on those strengths. This is what we get, which is less because we do have some strength in the problem. And then some results from V&V that Paul Suji did, where you have the cylinder with HC inside it. And then we also have a hubcap, the steel cap on top of some explosive, and we do the comparisons. Here's some results from the cylinder. What ends up happening is these SPH particles get far enough away from each other, the kernels don't touch, and the gas can jet through. Okay, because then we don't, when we're doing that, building that airtight surface, the particles can form gaps. And there's a result, compared to at some particular time. And qualitatively, it's all right. Here's the hubcap. You can see sort of these radial cracks. This is what from Visit, you can get a radiograph. Paul did all this work. And this is the actual radiograph, which qualitatively is pretty good. But actually, the results from the probe look really good. You have these probes, these velocity probes along the length and along the circumference, and the simulations match quite well for a range that we have. Same thing here, and all the different probes for the hubcap. It's pretty good for the SPH2. Not quite as well on the hubcap. There's some things we could probably look at to improve. So here we've incorporated friction lately and unilateral contact, so gaps can open and close. And so here we have this bar, it's a rebar. This is concrete, and then it's compressed by some plates. This is the damage that results as we apply a force to pull that bar out. And then you can see backfill basically from the concrete into the gap that's formed. This is the normal pressure along that bar, and for different Coulomb coefficients, the normal pressure is pretty much the same, and then drops off as the bar leaves the concrete. And then this is the friction at the different levels. So this is 0.4, this is 0.2, it's about half of that, and then this is hardly any friction. And so we have some more V&V to do with that. But now with contact problems, well, where we live, they're all dominated by all our problems. Engineering problems are dominated by contact. This is the only thing I can show, which is a transportation container. And so you can see there's lots of surfaces, and they're always concerned about the bolts. And this, we put all the contact in that. There's lots of versions of constraint enforcement, but the traditional one people use most of the time actually still is node to surface. There, a node can't penetrate a segment. From mesh 1 to mesh 2, and then you flip side the 2 pass. This node can't pass through mesh 1 segment. And then now particularly for implicit contact, people are using surface to surface contact because it behaves better. And so for mortar, you pick a pressure field on one side, And so when you run a patch test, just apply some uniaxial stress on these blocks. The single pass does terrible for the patch test. The double pass does better than this, but it's not perfect for 3D anyways. And if for higher order elements, it doesn't work even for that at all. But the surface to surface works pretty good. In fact, it's perfect for this problem. And so if you have, say, pressure, I have this beam as a sandwich beam. If I put enough pressure on it so that the contact stays active on this interface between the two beams, put a moment on it, you get, ultimately this curved result. If you twist it hard enough, and with the double pass, it just locks up because you have pointwise enforcement of this constraint, and it can't bend along that interface because we're pressing hard. But with the mortar, for instance, you get a weighted least squares gap, and that gap will actually allow a little bit of bending along that line. So, but again, the problem is you have to pick a side for the pressure, and so you can't do this self-contact problem. And so segment-to-segment approaches aren't biased, but they're typically not stable, but they still work for penalty methods. So like common plane, you have this segments based on, you put a pressure on them. In this case, it would be a penalty pressure, but you could do a Lagrange multiplier pressure. And so each segment, you can put a different pressure on it, say piecewise constant. Problem is if you under certain symmetry, you can have this plus, this high, low pressure on the segments that result, or a low, high. And since the forces at these nodes is just the average of these pressures, you're going to get the same pressures in the purple forces as you do in the red, which means I can't control that pressure. That thing could just show up. You won't see it so much with penalty, but you'll see it with Lagrange multipliers. Problem with two-pass mortar, and this is what we're going to fix, is now I'll add another pressure on top, but there, if you don't stabilize it, you can get a small pressure on top and a big pressure on the bottom, or a big pressure on top and a small on the bottom. And again, the contact forces that result are the same, so I can't control that. So that's what I'm going to do. So here's my shape functions. I model my I interpolate my displacements using them, and I'll also interpolate the tractions with it too, and a nodal traction is based on some scalar traction and some nodal normal that I choose. I have my test functions for displacement, and I also have a test function for pressure. And so when I put this into my abstract boundary value problem, I get these contact force terms. This is the energy, and this is my constraint term. Again, energy looks just like this, based on the strains. And constraints basically are the test functions for the pressure integrated against the jump and the displacement. And so when you put in the nodal quantities for this, you get a discrete form that looks like that, which gives you a nodal gap for every node on the non-mortar side that involves the nodal normal and again the jump that's integrated against these test functions, and that's the weighted least squares I was talking about, the weighted least squares gap. The contact forces come from the trial function pressures integrated against the test functions, and then this is the discrete form of that with the nodal quantities, and then you get nodal forces from that. You're going to get a system of equations that looks like this based on stiffness matrix, and these are the B matrices that basically give you the contact forces you see here. And again, if I use regular mortar method, I'll just use one pressure from one side, and it turns out these B matrices are then the columns are linear independent. So the pressure is going to be unique. I don't get a mode, but it's two-pass. These are linear independent, and so I have to fix that. So the way I fix that is I put in, just like before, I put this stabilization term in J into the abstract boundary value problem. And now again, I'm using two pressures on both sides, and the J basically uses gamma scaled by h to penalize the jump between the pressures on both sides. Now these are both oriented positive and negative. So basically, I drive this guy to 1, and I drive this guy to -1 to make them the same. Okay, because again, the sign is opposite. And so I want to keep them close together. Okay. By the way, that looks like it's biased, side 1 and 2, but I don't really need to pick a side 1 or 2. So say I have some impending self-contact between this bar here, and it turns out the way I do the integrals is I can project quantities. I split this up into 2 intervals. I project quantities from this side onto that side, and then quantities like integrals from the same segment. So everything's done segment-wise from this side onto that side. I do that up until I reach a fold, and I know what a fold looks like because basically when I project this segment onto that segment and this segment on that, they both share a node. So then I know I don't go any farther. So I don't have to do a decomposition into 1 or 2 or anything else. I just reach a fold and I stop. So the way you attack this problem to figure out the stability of it is you form the bilinear form from the individual terms, and it looks like this. And basically you have to satisfy an IMSoup on what they call the BNB, the Bretzi-Nikas-Babushka condition, and it's sort of a version of the LBB condition that fits in better when you have the stabilization term. And that's basically, given any trial space, I can find a test space that makes sure this thing's bounded from below. And it's effectively what I'm making sure that I get a unique solution to this guy, right? So the question is, though, what norm are we going to use, right? Again, all this stuff's in this paper from a couple of years back on all this. And so the way you pick your norm in this case is you make sure that whatever norm you pick, will bound this bilinear form from above. And it turns out that, basically by squaring pieces that are in that thing. So, obviously I'm going to get the H1 norm for this guy, right? But these other guys are weirder. So if I square, lambda in here, I'm going to get, really what I really going to get is a fractional norm, a trace norm, which is the 1/2 norm, but I'm going to use what they call mesh dependent norms. And this guy's even weirder for the displacement. It's the L2 projection of the gap. And I'll talk about that in a second too. Here's the gap. It's the L2 projection that shows up in this 1/2 weighted norm. So this is everything. This is a review. There's my bilinear form. There's my IMSoup condition. There's my upper bound. Here's my norm. And what I want is to use this ansatz, this set of test functions, to show that this guy up here, my bilinear form, is greater than 0. That's job 1. This is the breakout of all these terms here. And what I'm going to do is play the game where, okay, I know if I pick a test function that uses my trial function in here, that's going to square this guy, okay? And that's good because that's a positive term. But then what I need to do to square this term here, I choose the pressure at the surface and I actually extend it into the boundary 1 element. And that'll square this term for me on the surface. But it also shows up in this boundary, in this volume term. And what I got to do is use inverse estimates and or an inverse inequality and a Young's inequality and Cauchy-Schwarz, and I can show that if I choose beta small enough, this term doesn't mess me up. And so that's the game. And that's where it gets a little tricky. Same goes for here. For the test function for the pressures, I use the L2 projection for the jump. Oh, did I just totally skip? Yeah, sorry. I skipped what the definitions were for the mesh dependent norms. Basically, a mesh dependent norm is I'm going to have pressures integrated against, sorry about that, displacements, and then I'm going to come up with this -1/2 norm, which is the mesh size times the inner product for the norm of these pressures, and then 1/h for the displacements, and that satisfies this inequality because the h's cancel. And then the L2 projection is just, I have some function v, which is L2, and then I basically do a least squares solution which gives me this L2 because I project both against the shape functions, and I come up with this L2 projection based on this mass. So back to here. Sorry about that. So we already showed that guy squares a term. We already showed that guy squares that term. I got to make beta small so that the cross terms go away. Here I put in my L2 projection squares that guy, but again I have to make alpha small using those inequalities, Young's and inverse equalities. And then this guy squares that term, and so that basically makes that positive, and I demonstrated my bound, my in-soup condition. Okay, so now I want to come up with an error estimate, and so there, I have the exact solution for the displacement and the trial solution for the displacement, and the same thing for pressures. And I use my triangle inequality, and when I want to figure out what this term is, I can use my bound, because that's what that in-soup condition did. I can replace it with the bound, okay, and this is the lower bound for that bilinear form, and now, if you might remember from your finite element class, that if you just had no constraints, you have the energy, you can show that the energy of the error is zero, right? It's an orthogonal, it's a Glorkin orthogonality. You get something very similar with this, and I'm not going to go through the process of showing you, but I know what the upper bound is, this guy, that's M, and I, just like here, I can replace UH with U and basically get a best approximation, because V and mu are arbitrary, and so that looks like best approximation. And then now I can apply my estimates, my error estimates. So for the displacement, I just use the L2 norm, and I know that scales with h squared for h2, and for the h1 norm, that scales with h. But for the mesh dependent norms, those are weird, remember? And it turns out in the literature they also have bounds for those, for the displacement and the this should be a -1/2, and for the pressure. So I put these estimates into here, and I can now come up with my optimal order energy norm for this, for my solution. And so now, when you look at this matrix, it doesn't look like you see, because you have this weird J in here. And how does that fit into the KKT conditions? Meaning, I need to get a solution to an inequality problem, right? Well, anyways, I get this matrix that looks like this from that, and I want to come up with what my scaling parameter is going to be. So I can, under suitable conditions, condense this matrix out and just, solve the dual problem for lambda. And I'm going to size J by this gamma, as I mentioned, this gamma. And it turns out, based on scaling arguments, I just need to scale it with some, any parameter, positive parameter, divided by some characteristic stiffness. So 1 would turn out to be the sweet spot, because it basically makes this sort of on the same order of that. Anyways, this whole thing comes from a minimization from this energy function. But in this case, how do I, I'm trying to force this guy to be 0. What is this? I have the pressure in there. So how does that work with the KK conditions? Well, it turns out I can play a game where I incorporate another variable, J mu, which equals J lambda. This is a different mu you saw before. And now everything looks just like the usual KKT conditions. I have some function I'm minimizing against this constraint. And so this constraint actually sort of has this weird mu built into it, but really that mu is just the pressure. And then I get a system that looks just like the KKT conditions, which now I can use as an existence for some solution where this gap can be open and this pressure could be non-zero. And these are usually complementary conditions on those. So now the results, I get no locking with that, in that particular problem I showed. Now I have this curved interface on a beam that I'm shearing. I get nice smooth pressures for the bending field. I get nice smooth pressures for the shear field. This is that curved interface here. And then, I show optimal convergence in the error norm for a range of scaling parameters. Here's a pressurized sphere. I get, again, this is the effective stress. It's nice and smooth. Optimal convergence, in this case, displacement norm scales with h squared. And then, the Hertz problem, I have a fine mesh on the bottom. I get the contact pressures, and this is black is exact, and I get very good answers for this range of alpha. And then here's some nonlinear problems, and so I have some hyperelastic rubber here. I have some plastic material for this cylinder buckling, and I mean this looks like an easy problem for an explicit code, but it's definitely not for an implicit code. What ends up happening is I load this column, this rubber column, the force goes up as this thing basically gets compressed into a ball. And then here I had, these lobes as I push on that cylinder. These lobes are basically little buckles, and as these buckles start to coalesce, they start to get stiffer, and then I form a new buckle, and then so on and so on and so on. And then once it gets down to the bottom, it's very stiff. So again, not an easy problem for an implicit code. And so I couldn't do that with my regular word. So here, what I have is this rubber beam. I give it a push, so it turns out it's translating, and it's also rotating at a relatively good rate. And just using Newmark's trapezoid rule, which people almost always do, it doesn't work for large rotations. Basically, a lot of these time integrators are unstable for these nonlinear problems. And this would be the velocity in that one of those nodes. It just eventually goes crazy. Here I have a block which I give initial velocity that's basically in between two other rigid blocks, and eventually using this Newmark's method, it just goes. This is a linear material. It just goes unstable very quickly. And so to fix all that, we're going to use these structure-preserving time integration schemes, and they're second order. A higher order scheme, in fact, you may not be able to conserve anything with a higher order scheme. They may work better, but you can't prove as much for these nonlinear problems. And it turns out these are good for long time events. So, you can enforce discrete energy momentum, or you can do, like symplectic time integration schemes with which conserve this phase space of the energy. So the equations of motion we show here, these are the internal forces, these are the contact forces, and using a mid-step time integrator, basically the displacements in terms of the average velocities. And so if I take these velocities, as you see here, and multiply them times this inertia term, I just basically get the difference in the kinetic energy. This is the mass matrix. It could be a consistent mass matrix, for instance. And I take this and just multiply it times the forces, and I get basically what looks like an energy term, right? You get a displacement times the I mean, you won't get anything like this with Newmark's method. And so under computing the internal forces the right way, this is the second pK for stress, and if I compute it based, for instance, for the simple elasticity model on the average of the green strain, I can use other material models, but you have to do them the right way. Say for the case where I have zero contact forces, you can show, these are classical results, that the linear momentum is conserved. Basically, the inertia at time n plus 1 equals the inertia at time n, because the sum of the forces in the system sum to 0. Same thing here for angular momentum. I get these discrete forms of angular momentum. I cross product of the coordinates with the inertia is basically 0 from time n plus 1 to time n, because again, the moment formed by all these internal forces is 0. And then the same thing goes with the energy. The internal energy at time n plus 1, or the total energy at time n plus 1 equals the total energy at n. And these are the inertias, and these are the strain energies. The inertias are basically always positive because the mass matrix is positive definite, and this term's always positive because my elasticity tensor is positive definite, and this is in terms of displacement. So basically, this constant energy, say I have no applied loads, This thing's just, wiggling around in space. It bounds these velocities and bounds these displacements because of the positivity of these terms. So you get this thing called B stability, meaning that I can bound some terms, some metric, and make sure that they don't blow up. Relative terms don't blow up. So now I got to show that the contact forces observe the same conservation. So you get these constraint matrices G to get the forces. You get the same thing for the gaps. Basically, you're integrating the pressures against the normals and shape functions to get that G matrix. And I want my gaps to be positive. I want my pressures to be positive. And it turns out as a result of how we do the segment projection scheme, that the sum of all the forces, contact forces, add to 0. Okay, I'm not going to show all what's involved with that, but take my word for it. The same thing, if you choose the contact normal the right way, you can show that the moment of all the contact forces is 0 too. And now I'll talk a little bit about the energy. So basically, remember, you get that energy related term that pops out of the mid-step time integrator, and the energy of the contact forces at contact is dissipative. So what ends up happening is I have a node here. Say it hits the opposing surface, and it goes through this vertical displacement to get there, but the force is up, and so the displacement dotted into that force is negative. So I got energy being dissipated. This Ka is positive. Okay. Now it's a 3-step process. First, I solve for these velocities and these pressures from that equation of motion. Okay. Now I want to compute a velocity update, and I'm free to do that as long as I make sure that the energy is good. I want to enforce this gap velocity constraint, meaning that the gap formed from the very velocities themselves is 0 to avoid contact shatter and to provide dissipation. If I don't do this, I'm able to maintain that contact that you see above, but that velocity will just bounce up and down. So my new velocity is not going to do that. So the way I do that is I balance the impulse of the new velocity with the old velocity, or the inertia, and use a new multiplier to enforce this gap velocity constraint. Now this is just a linear equation. It's a linear equation with a constraint, and then based on this simple identity for the updated velocity, which is just in terms of itself and the previous velocity here, I can show that this whole velocity update is strictly dissipative. So I take this velocity, use this identity, dot it into this inertia term as you see here. Since this term drops off because of the constraint, I push everything through, and I show that my kinetic energy using my updated velocity is the same kinetic energy as before, minus this term here, which is strictly positive. So now my new energy, if I use this, is less than my old energy at time n. Okay, that's not a bad thing. This is basically like a plastic contact, but I may want to give it back depending on my situation. So as before I said, when you have just initial contact, you get some dissipation. And basically this is a plastic dissipation, like you see with rigid body analysis. When the two rigid bodies hit, I might have a plastic contact, and so the velocities at the interface basically will be the same, right? And so with the plastic dissipation, I can show how much energy is basically dissipated in that, just based on again, it's always dissipative based on the forces that result from that. I compute at each node the dissipation, and then I can add the initial dissipation plus this dissipation during the plastic impact, and this is how much I need to return to the system. And I only return it when I know that I'm releasing. So again, these are all kind of a post-process step. So I know when I did the equations of motion, I knew this thing was releasing. So now I'm going to give it back. I'm going to give the energy back. I'm going to compute a new velocity update based on my previous velocity update with this force term that's related to that constraint, contact constraint matrix times these times the energies at those nodes, at those slave nodes, or I can't say slave node, non-motor nodes. And based on the scaling parameters you see here, which is in terms of the total energy. And it turns out that this whole thing is well behaved because the numerator that results from this is always smaller than the denominator. And then what I can show is basically that the kinetic energy for this update minus the kinetic energy with this other update returns all the energy back to the system. So now with my new time step, I have all my energy back, and I reset my velocity for the next time step to be that last update. So now I combine that problem I had before where I had these rubber boxes, and I'll put a new rubber box in between. I'll give this guy a kick, and basically he hits the other box inside there, and this thing bounces around 1,000 times. And I run it out for 20 seconds, which you can never do in an explicit code. And what I show is, the total energy is conserved over the whole time. The kinetic energy here, shown here, the internal energy is here. This is for the fully conserving version, where I give all the energy back. Here I'm giving the energy back, but I have friction, so that's going to give me some natural dissipation in the total energy. Here's the kinetic energy, and they go down rather slow. But with the plastic impact, you can dissipate a lot of energy. And in a lot of systems, you really don't know how much energy you're going to dissipate. And you can pick say a coefficient of restitution that may give something back in between here and here. In fact, that's how everybody always solves all their problems. When they know they have damping, they tune it. And what ends up happening is, as you run this thing out long enough, out to say, like I said, 20 seconds, that one box finds a corner and it just sticks in there. For the conserving version, it kind of wiggles around in there, but for the plastic one, it just locks right in. But meantime, even though you have dissipation, the angular momentum stays constant. This discrete form of angular momentum stays constant throughout the whole time for all these different cases. So that's what you want. So if I got some space vehicle or something like that, I don't want this thing to stop rotating or go rotate into some weird phase because I can't conserve that quantity. So to sum things up, we developed this immersed finite element approach called fusion that couples AL and SPH. We use multipliers with stabilization to do that, and a special advection technique. We stabilize the two-pass motor context so we can do self-contact. And then we come up with a structure-preserving time integration for the contact that makes it stable for implicit time integrators. And now what we're working on is a GPU port of fusion, and these folks are working on that, and then a GPU port for tribal, and these folks and others et al. Are working on that. The domain decomposition for slide world, which is also really fusion world too, is where Ben Liu and Eric Chin and Kenny Weiss are working on that. That's some of that's done for the blast code, but it's not done for the implicit side. We're currently working on topology optimization with contact with Lido, Smith, and Diablo, and we have a paper out from a couple of years ago on that. And one of the interesting problems that they're trying to model there, Todd Weisgraber is trying to do for additive manufacturing, is the size of these nylon plies, but they're all in contact like these Lincoln logs you see here. And there's a lot of contact. It's a very hard problem. There's a proposed LDRD by Cosmin Petra that's going to develop scalable methods for contact and optimization. Basically, they want to come up with better regularization techniques for the semi-smooth Newton and interior point methods using algebraic multigrid. And I think that's going to be an important work. We're also modeling on fluid sorption across interfaces, which is basically a coupled diffusion thermal structural problem with contact. And basically what you end up having is you might have these rubber materials and they can trap fluid inside them. You can get sorption inside there, and you can also get sorption across these interfaces. But sometimes you might have like open areas where the gas gets trapped and it can't go into the bulk nodes. And we can actually capture that, like in 2D. Obviously, you can't pass out through this trapped inside there. In 3D, we can even do the same thing. We can try to find a path to the boundary. And if there's no path, then it doesn't basically contribute to the bulk node humidity. And that's headed up by Stephen Costagaway, but the MGGR group, method development group's working on that. We've implemented multi-component ROMs in MDG, but we haven't put contact in them. Rishi Garnawala was working on adaptive meshing with contact, and we have that in our test suite, but we haven't put that out for public consumption yet. And then we have a two-way thermomechanical contact that incorporates the Joule-Goff effect. And that's basically, I have this, say, body in space, it gets hit by a thermal pulse. You get this thermal expansion, and then you get this vibration. Now this thing cools, but the thing's still vibrating. So where did that energy go, right? Well, it turns out that there's a dissipation mechanism that we typically don't model in this one-way coupling for thermomechanical simulations. So we bring in that dissipation effect, and we have a CGSF fellow, Justin Porter, we're going to work with in our group that's putting that in to basically be consistent on the energy. So that's pretty much it. And I'd like to entertain any questions if there's any.
Thank you, Mike. That was a very wide-ranging talk, but I think it showed a great overview of this work that's going on at the lab. So, any questions? Either feel free to take yourself off mute or put it in the chat.
There's a lot of stuff. I know. I went through it so fast. Sometimes people can space out when you see that much stuff.
I do have a question. This is Cosmin. Can you go back to the slide where you use that J as a regularization for the contact problem? Right. This. Yeah.
Oh no.
Yeah. That one.
This slide or
where you also introduce mu in on top of lambda.
Like here? Or earlier?
I think it was 55.
55. Oh, okay. Okay, there. All right.
Oh, maybe not.
Maybe next one.
There?
Right. This one, yes.
Okay.
Out of curiosity, why can't you just solve the system with the 2-2 block? And why do we have to
I do solve this. But the problem with that is you can't use augmented Lagrange for that, for instance. You need a 0 in the bottom block to do augmented Lagrange.
Oh, right. Okay. I see it. Yeah. Because
and in fact, a lot of solvers might want that 0 there too.
Yeah. But yeah, it's that J block. It's really need to do a regularization.
Yeah. So this J block right here. This isn't good, but you can stabilize this J block if you really want to use this for the solution. And it turns out you can stabilize this J block and still get this if you know what eigenvector to stick in there. And we sort of do know what and so if you stuck the one eigen, because basically this thing is positive semi-definite. So yes, that is a problem there. But if I stabilize that by incorporating another eigenvector, which I know, I can make this invertible and still satisfy this.
By incorporating another vector, you mean adding the identity multiply with the eigenvalue?
The identity would work, and you can get that. You're not going to get this back, but it'll still be good. If you added, say, a block of ones, just all ones, because it turns out that the constant passes through this thing. So like a vector of ones passes right through. So that means that's my eigenvector that it's missing. And so I can basically do an outer product of that eigenvector and add it into this and stabilize this and then satisfy this system and still satisfy this because that eigenvector doesn't live in this range space.
Thank you.
That makes any sense.
It does, yeah. Thanks.
It looks like Jerome had a question or a comment. He says, one thing that's interesting to note is that the dissipation is necessary to avoid chatter. can't get rid of the chatter by reducing the time step. And he gives an example of two rigid bouncing balls that you have to conserve the energy by making the balls bounce without dissipation.
Yeah, I mean that's what people end up doing is they to get rid of the chatter they add dissipation, but the dissipation ends up you killing the problem, and it turns out it still can go unstable because you don't know how much dissipation to add, and there's no guarantee. So if they use the Newmark method with dissipation, it will still go unstable. So yeah, I didn't show an example of where you get the chatter. As you can see, the chatter is controlled by this here. And again, this nice thing about this is it's linear problem. It's a linear problem that I do after I solve the nonlinear problem.
Any other questions for Mike? Sure.
So first of all, Mike, thanks a lot for coming and presenting. This is so much impressive work. It's a bit overwhelming, I will admit. It's you guys have really done a lot of things.
It's basically 3 talks that are all smushed together.
Yep. But yeah, we absolutely we wanted to broaden the seminar to include a lot of engineering perspectives like this one too. So going back to, can you go back to the slide 56, the one that Cosmin was discussing?
Yeah, sure.
Okay, so regardless of which exact formulation you have, with additional stabilization on that, you have a pretty complicated system. And I don't know, maybe I missed it, but did you mention how those systems currently are being solved?
Right now, I'm just using a direct solver, and the direct solver still has to pivot because of this term. It's
Right.
not positive definite, and so it works. It doesn't do exact pivoting for the big parallel for the distributed memory parallel, because it's really hard to do exact pivoting in distributed memory parallel. So they come up with an approximate type form of pivoting. So that's the reason why I don't use this very much right now. Is it doesn't even these direct solvers kind of gag on that when they're big parallel distributed memory solvers. The ones that are that do full pivoting work fine. So this thing doesn't get this doesn't get you out of the woods as far as the solving an indefinite system. That's the issue.
Right. Okay. I just wanted to clarify that. Yeah.
Can I ask a question?
Yep.
Okay.
Absolutely.
All right. So this slide is fine. I was just wondering, because you have the second equation, right? The small b minus the small j, and the small j is like you're adding something together, if I remember correctly, the definition. It's like an average of on the two surfaces.
I got a pressure on top and a pressure on bottom, and
Right.
They're different signs. So basically, I want to force them together. So if this is +1 and I want to make this one -1, and I'm using gamma to do it, and I have to scale it by h, as it turns out. I mean,
okay,
because of the way the scaling laws work within the when you're enforcing this in soup condition. That's where you find out that that's how you scale it. That's sort of the mechanism.
Okay, so
it goes away. It goes away as you refine the mesh.
You mean the h goes away?
Well, the h gets smaller and smaller. It's
okay.
It's basically
okay. You mean the j term goes away? I guess.
Yeah, the j term goes away.
Oh, okay. So the b minus j is just the is it the impenetrability constraint? Is that the contact constraint?
Yeah, well, it becomes a contact constraint, and it's a subtle thing that shows up here. Basically, the b minus j is here.
Right.
I don't, usually it's just b times u that gives you the gap, right?
Uh-huh.
But now it turns out,
right.
The KT conditions tell me I need to leave that in there. I need to leave that pressure in there. And so this whole row, basically, the gap is basically this term plus that term. So it has this pressure dependent term
Okay.
in the gap when you're doing these
Is-
stabilized methods.
Is that how you come up with this, Jay? I'm just wondering, like, how do you get this? What's the intuition behind defining?
Well, the form of J
Yeah,
was basically, as I mentioned,
right.
these
It's
mu-
just
if you look at this as an energy, this would just
Uh-huh.
be, say, this is after the variation. These are
Okay.
test functions. This would just be lambda plus 1 plus lambda 2 squared. That would be sort of like the energy term from this thing.
okay.
And so when you take the variation of it to come up with the equations, the first variation,
Mhm.
and the miniation, the gradient, you get these test functions terms. But basically, this guy is keeping these lambdas close together.
Okay.
Because of the gamma. And like I said, it's more obvious when you show it in the form of energy.
Okay. Okay. But this is not like a it has to be this term. It can be some other forms.
Well,
This is just-
you could have cooked up a different term. And
Okay.
if you're using a different type of surface to surface approach, you're going to use a different term. If you say use that piecewise constant segment approach, you'd have to stabilize the pressures a different way. Say stabilize the adjacent pressures. Either way, you're going to land with some stabilization term.
Okay. Okay. Thanks.